Hi there. My name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is the datasheet for the SSI2144, which is a 4-pole voltage-controlled filter that's based on the original SSM2044, which, according to this great write-up on the Electric Druid website, was used in a bunch of Korg synths like the Poly 6, the Monopoly, and the Trident, as well as the PPG Wave 2.3. The typical application circuit shown on the datasheet shows a schematic along the lines of what you might use in a standalone module for a modular synthesizer. But I would like to think about driving it using a microcontroller like the Adafruit M4 Express series. And notice this Grand Central version in particular has a whopping 22 PWM outputs. The frequency control input is pin 15, so you can see that here. And if I scroll down a little bit, I see that it has an input range of minus 120 to 150 millivolts. So I don't know if that is sort of meant to be an absolute limit of the input range, or if it's meant to be a sane range of operation. Because if I scroll down to the absolute maximum ratings, it doesn't give any sort of information about that. Now, if I look at other places on the datasheet, that frequency control input is often spec'd as having a range of minus 90 to 90 millivolts. So you'll see that here, and you'll also see that here. So I'm going to take that as vaguely my target range. Notice this line in the datasheet with values shown in figure 1 plus minus 90 millivolts at the frequency control pin correspond to a 1000 to 1 sweep range using plus minus 12 volt supplies. So that sounds good. Now there is this note here. A frequency offset adjustment is necessary in polyphonic systems for consistent cutoff frequency across voices, or programmable systems where repeatable performance from a given control voltage is desired. I want to really avoid using trim pot, so let's suppose we can actually do some sort of calibration in software where for a given value of desired frequency, we could send different voices slightly different voltages as needed. Okay, so here's what I'm thinking. Suppose this is the output of the microcontroller, and I'm going to assume it's an ideal voltage source. We'll come back to that point a little later. And let's suppose over here I have the input to the 2144's frequency control. I'm going to assume that this is a high impedance input. Actually, let's check that. Let's see, there's no input impedance measurement given, but I see input bias current for the frequency control, 4 typical or 10 max microamps. Okay, so I'm just not going to worry about that. Okay, so I would like to do this without using any op amps if I can. Now, we know that 3.3 volts at the output of the microcontroller, this is assuming that we're using a PWM output on a 3.3 volt microcontroller, so that will max out at 3.3 volts. That needs to correspond to something like 90 microvolts over here on the 2144 side. So we know we're going to need some kind of voltage divider. So I'll put a resistor here, and I'll put a resistor down here. Now, at the other extreme, we can output 0 volts from the pin, and that needs to correspond to minus 90 millivolts. So to be able to get this negative voltage, let's throw another resistor in here, and let's connect it to the negative power supply rail. So I'll call that VNP. And we need to pick something for this. So how about let's use minus 12 volts. That's the Eurorack standard. I personally like the plus minus 15 volt standard of MOTM and Blasset, but the Eurorack standard kind of won out, so people are more likely to have a minus 12 volt supply lying around. Okay, let me call this resistor RMC, and we'll call this one RNP, and we'll call this one RG for going to ground. Now, you might be tempted to write the formulas for the circuit using your standard voltage divider rules for resistors, but once you have more than 2 resistors involved in a junction like this, I find it easiest to actually think about it in terms of conductances. So let me write 1 over GMC, and I'll write 1 over GNP. That's a G, not a 6. This is 1 over G sub G here. And so these are the resistances expressed in terms of conductances. So I can write the voltage at the frequency control input pin using a superposition sort of argument for the different voltage sources here. So I'll have VMC, and here you'll see why I really like this conductance kind of formulation. So I'll have the sum of the conductances in the denominator. So I have GMC plus GNP plus G sub G. And now in the numerator, I write the conductance, GMC, associated with my voltage source. Now, if you plug in 1 over R for these various sorts of quantities, and you then try to simplify the fractions there, you wind up with resistance times resistance plus resistance times resistance plus resistance times resistance, and there's a resistance times a resistance in the numerator, and that winds up being very difficult to reason about. Now, if you really want to think about resistances and traditional voltage divider rules, you could think about parallel combinations. Like you could write this term as something like R and P in parallel with RG all over RMC plus RNP in parallel with RG. And then if you spell out these parallel combinations and do a bunch of algebra, you'll eventually get this. But I think it's easiest to just start here. Okay, so let's see. We need the term for VNP. So the voltage divider for that is going to have all the same stuff in the denominator. GMC plus GNP plus G little g. And let's see, in the numerator we'll now have GNP, because that's what's associated with our VNP, and I forgot the N, so let me put the N in here. There we go. Plugging in 0 for VMC and minus 90 millivolts for VFC is going to give me one equation. And plugging in 3.3 for VMC and 90 millivolts for VFC is going to give me another equation. So that's two equations. And at first you might panic thinking, hey, but I have three unknowns. But if you look at this, it's a ratio. So I could take all of the resistors and scale them up or down uniformly by a constant and get basically the same circuit. So let's suppose that you choose G sub G ahead of time, and we'll say that GMC is equal to some constant alpha times GG, and we'll say that GNP is equal to some constant beta times GG. And now we're looking for alpha and beta. All right, so VFC is going to equal VMC. And when I plug these formulas in for GMC and GNP, I'll have G sub G's on every term, and those wind up canceling. So here I'll have alpha over alpha plus beta plus 1. And then I'll have plus VNP. And then for the next term, I'll have beta over alpha plus beta plus 1. Okay, so let me multiply both sides of the equation by alpha plus beta plus 1. So on the left, I'll have VFC times alpha plus beta plus 1. And then on the right, I'm going to have VMC times alpha. And then I have plus VNP times beta. All right, so I want to have all of the constants on one side and all the alphas and betas on the other side. So the only constant I really have here is the VFC on the left-hand side from VFC times 1. And when I have VFC times alpha and beta and move those over to the other side, let's see, I'll wind up with VMC minus VFC times alpha. And then what else? I'll have VNP minus VFC, all of that stuff. Whoops, I forgot the C there, times beta. Okay, that's the worst FC anyone ever wrote, but you get the idea. Okay, so let me plug in the values needed to get my two equations. So for the first one, I'll write 0.09 volts with a minus sign on the left here. And then on the right, well, VMC, that's going to be 0. And then I have minus the same thing, minus 0.09 alpha. And let's see, VNP is minus 12 volts. And now I'm going to subtract that minus 0.09. And let's see, this is all times beta. I have minus 0.09 equal plus 0.09 because the minuses cancel times alpha. And then let's see, this turns into a plus 0.09. And when I combine that with the minus 12, actually, let's see, that's going to give me not a plus, it's going to give me a minus 11.91 beta. Let's see, I would like to make some more room, so let me grab this here and scoosh it down here. Okay, let's see, for my other equation, I'll have 0.09 volts, that's this one here. And on the right, let's see, VMC is going to be 3.3 volts. And now I'm going to subtract that 0.09 volts. That's all times alpha. And let's see, I'll then have my minus 12 volts. And then I'm going to subtract 0.09, and that's all times beta. So let's see, I'll have 0.09 equal 3.21 alpha. And then I'll have minus 12.09 beta. All right, so here are my two equations. Here I have one equation, and here I have another equation. And I need to solve those two equations for alpha and beta. And for that, I'm going to use Octave, which is an open source rewrite of MATLAB that I strongly suggest you download and check out if you haven't. Okay, so here's Octave, and let me define a matrix MAT that contains the coefficients for alpha and beta. So I have 0.09, and I'll put in a space, and then minus 1.91, and I'll put a semicolon. And Octave will interpret the space here as indicating a new element along the row of an array, and the semicolon says go to the next row. So in the next row, I'll have 3.21 and minus 12.09. And let's see, what I'll do is I'll take that matrix and invert it and multiply it by a column matrix containing 0.09 and 0.09 without the minus, so that's this here. Oh, right, I need to put a quote here, a single quote to transpose that matrix to actually get a column matrix. And I wind up with these numbers. Now, remember, alpha and beta are in terms of conductances. Now I want to start thinking about resistors. So let me take 1 divided by the answer. And what this dot division does is it does an element-wise divide. You can do the same thing with the multiply. If you just do the star symbol, it's a matrix multiplication. But if you do dot star, then it's an element-wise multiply. Anyway, that gives me factors of 17.196 and 125.061. And let me call that something. I'm going to call it AB for alpha beta. And let's let that equal our answer transpose like that. So what I'm going to do is I'm going to try some resistor values and see what kind of values I come up with, because I want some resistor values that are things I can actually buy off of Mouser. So let's try 120 ohms, and I'll multiply that by AB. And let's see, what if I were to take this one here and round it to 2K, and take this one here and round it to 15K. That seems reasonable. Okay, let's go to our Google and look up common resistor values. All right, let's try out this first hit here. Continue to cite, and let's see. So we're no longer in the age of 10% resistors. For 5% and 1%, we have 12 as a starting number, so that's for our 120. And 15 as a starting number, so that's our 15K. And we have 20 as a starting number, so that's our 2K. So I wrote an Octave script to test things out. I'm setting VNP to minus 12, RG to 120 ohm, RMC to 2 kiloohm, and RNP to 15 kiloohm. Ignore the stuff here that's commented out. I'll come back to that. I compute the conductances that are the reciprocals. I compute a denominator. That's all of the stuff down here, this alpha plus beta plus 1. And then I compute the voltage at the frequency control for a VMC of 0 and a voltage at the frequency control for a VMC of 3.3. Okay, let's try that out. So I'm going to say VFC to run that script. I get something pretty close to minus 0.09, and I get something that's above 0.09. It's above by this amount, but I think that's okay. If you take a look at the 2144 datasheet and look at the range for the frequency control input, it goes from minus 120 millivolt to 150 millivolt. So there's a little bit of extra here on the positive side. So that kind of matches. And while I have the data sheet up, something else I wanted to mention, remember we have an inverting op-amp configuration in figure 1 here. We don't have something like that in our design. So the control of the frequency is going to be flipped from what you usually expect. So low voltages are going to correspond to high cutoff frequencies, and high voltages are going to correspond to low cutoff frequencies. But that's all okay. This is all being taken care of in software. Okay, so what was all this about? Well, let me uncomment these lines. And you'll see I'm using this dot star. So this is an element-wise product. And actually, come to think of it, I don't need the dot star here, but I do need the dot star down here and the dot divide down here. So what I'm going to do is I'm going to do this computation for a bunch of cases at once. Oh, wait a minute, I messed up earlier. These should not be 0.01s here. These should be 0.05s. One moment. Okay, I got that fixed. Anyway, if you look at what I'm multiplying by, you'll see that I run through all of the extreme combinations of a 5% tolerance one direction and a 5% tolerance the other direction. Oh, whoops, I had another brain glitch. Actually, I have twice as many cases as I really need. There's 2 to the power of 3 combinations, so I really need 8, and I have 16. So these are doubled, but whatever. Okay, let me run this and see what kind of values we get. Whoop, that did not do what I wanted. Let's see. Let's go this way. And let's run that again. All right. So let's see. This here is going all the way down to 0.078. Not sure I like that. Not that I have a particular reason not to like it. I haven't really thought about it that much. So I'm thinking 5% resistors might be a little too loose. Let's go with 1% resistors. So that's this set here. Let's see, I need to comment these guys out. All right. Let's see now if I run that. Whoop, VCF. What did I mess up? Let's see, RP. Oh, this is RNP. RNP. There you go. All right. Nope. Oh, wait, what am I doing? VFC. Okay. I'll get with the program one of these days. Okay. This is looking a little more along the lines of what I'm thinking in terms of the various extremes. Let's see. If I go back this direction. Yeah. Now I would like to think about the fact that our microcontroller is not an ideal voltage source. Let's see how much current it might need to provide. So let's see, dropping across the resistor RMC, I'll have 3.3 minus 0.09 volts. That's 3.21 volts. And let's see, we'll pull out Ohm's law and divide that by RMC, which is 2 kiloohm. And so that gives me 1.6 milliamp. And this is the datasheet for the microcontroller used in the Adafruit Grand Central Station M4. And it is huge. It is almost 2,000 pages long. Anyway, on page 1805, there's a section on I/O pin characteristics. And apparently you can set a drive strength bit that changes some things. And on the drive strength setting that has the lowest milliamps listed let's see, we have 2 milliamps for this drive strength equals 0 setting for a usual voltage VDD in the range of 3.3 volts. So let's see, that 1.6 milliamp we computed is less than 2 milliamps, so we're safe. Although usually I would want a bit more clearance than that. So if you wanted, you could maybe double all of the resistor values we computed. But I'm also not sure I'm reading the data sheet correctly here. That 2 milliamp, 8 milliamp, that seems awfully low to me. I'm not sure. If you have some additional insight on this issue, let me know in a comment. But we're not quite done yet, because remember, we're driving this with a PWM signal. So we need to introduce some filtering to get a nice DC value out, but not too much filtering so we can slowly change that value if we want. So we need to choose a capacitor C going to ground, and if we didn't have RNP here and RG here, this would just be your standard one-pole RC filter, but we have this other stuff, including this attenuation, so it's a bit more complicated. Now the cutoff of this one-pole filter is going to be 1 over 2 pi RC, but what's R? So R is going to be the Thevenin equivalent resistance seen looking this direction. So you can imagine grounding out all of our voltage sources, and essentially what we would see would be these resistors all in parallel to ground, and that's going to be dominated by RG. We pick that to be 120 ohms, and in retrospect, that's a pretty small number. We might wind up wanting to scale up all of the resistors so we don't have to use a capacitor that's too big, but I don't want to think about that in more detail now because this video is already pretty long. Another thing we could do is potentially turn this into a two-pole filter. So we might take this resistance RMC and actually split it up into 2 different resistors. And I would probably have the second resistor be a lot bigger than the first resistor, but choose these so they add up to the same total resistance. And then I would drop another capacitor here, and let's see, we might call this C1, and we could call this C2. Actually, this whole formula here gets a bit more complicated if you really wanted to accurately model what's going on. But basically, by choosing these values well, like if I were to choose the resistance of this second leg here on the right to be a lot bigger than the resistance of the first leg, I can sort of basically compute 2 time constants, one associated with C1 here and another associated with C2. And the fact that this resistance would be a lot bigger would mean that I could sort of analyze the first resistor and the C2 here without worrying about how the rest of the circuit is loading it down. And in retrospect, I probably should have called this C1 and this C2, but whatever. I'll think about that another time.